Hello and welcome to my presentation on atomic structure and bonding. Today we'll be discussing ions, ionic bonding, covalent bonding and coordinate bonding, as well as a few examples of covalent bonds. And it will be covering scenarios 3 and 4 by Saffron Farrell Horn. Scenario 3 reads, atmospheric ions are electrically charged particles which occur naturally in the atmosphere. They form in the upper atmospheric layers, mainly because of the attraction of ultraviolet radiation from the sun, as well as in lower atmospheric layers as a result of radioactive radiation and cosmic rays. These cause ionization of neutral molecules or atoms. As a result, ions are formed. These ions instantaneously combine to form molecules with ionic bonds. Ions. What are ions? An ion is an atom with more or less electrons than protons and therefore has a charge, either positive or negative. Here we have a neutral atom. When it loses electrons, it becomes a cation, which is a positive ion. When it gains electrons, it becomes an anion, which is a negative ion. How are these different from an atom? Well, atoms are neutral, containing the same number of protons and electrons, whereas ions is an atom with more or less electrons than protons. Ionic bonds. What are ionic bonds? The ionic bond is the electrostatic attraction formed between oppositely charged ions, which occurs in all directions. The overall charge of any ionic compound must be zero. In this example, we have lithium forming an ionic bond with fluorine. Here, lithium loses an electron, becoming lithium plus. As it's lost, it's become positive, and fluorine becomes negative as it's gained one. So non-metals lose an electron from their highest energy level, becoming cations, whereas metals gain an electron from another atom, becoming anions. And here we have the electronic configuration of the atoms. So here we can see in the S subshell we only have one electron, and in the P subshell we have 5. An S subshell needs 2 electrons to become full, whereas P needs 6. So by ionically bonding with fluorine, we're losing this, so we no longer have an unstable subshell. And here we are gaining one, becoming P6, which is now a stable subshell. Scenario 4 reads, a polymer is a substance which has a molecular structure comprising of a large number of identical molecules covalently bonded together to form long chain structure. Many synthetic organic materials are polymers, such as nylon, polythene and Kevlar. Covalent bonds. What are they? A covalent bond involves the electrostatic attraction between the nuclei of 2 atoms and the bonding electrons of their outer shells. You can either have a single, double or triple covalent bond. A single is 1 pair of electrons, so 2 electrons total. A double covalent bond is 2 pairs of electrons, so 4 electrons total, and a triple covalent bond is 3 pairs of electrons, 6 electrons total. Covalent bonds only occur between non-metals. Electrons are shared rather than being transferred, like in ionic bonds that we saw earlier. Properties of covalent bonds are that sharing electrons allows both atoms to become stable at the same time. They're poor electrical conductors. If they're a solution, they do not conduct at all. And they have low melting and boiling points as a gas, solid or liquid, unless the substance is a giant covalent structure. So here we have a covalent bond between 2 chlorine atoms. So previously, chlorine has 3 shells. 7 electrons are located in its outer shell. Due to the shell not being full with 8 electrons, this means that it's unstable. By becoming a single covalent bond, they share 1 pair of electrons, and now their shell, both of them, have 8 electrons, making it a stable molecule. Here we have carbon dioxide. This is a double covalent bond there's a double covalent bond between both of them. So there are two double covalent bonds. As shown here, this is the symbol for a double covalent bond. Both oxygen atoms and the carbon atoms now have 8 electrons each, making it stable, whereas before oxygen only had 6 electrons in its outer shell and carbon only had 4 in its outer shell. These pairs of electrons that are non-bonded are called lone pairs. Here we have nitrogen. This is a triple covalent bond as showed by that sign there. And we have 3 pairs of electrons shared between both the nitrogen atoms. And both of the nitrogen atoms now have 8 electrons each, making it stable, whereas before it had 5 electrons rather than 8, making it unstable. Here we have ethane, which is a bit of a more complicated example. So we have 4 hydrogens, which are covalently bonded to carbons, which are both covalently bonded. So between the carbons we have a double covalent bond, and between each of the hydrogens and the carbon we have a single covalent bond. As discussed earlier, hydrogen, due to it only having 1 electron normally, and it being in the first shell, it only needs 2 electrons to become a full shell, which is gained by becoming covalently bonded, whereas carbon, this is its second shell, so it needs 8 electrons in its outer shell, which now it has obtained by becoming covalently bonded with 2 hydrogens and 1 carbon. Due to the sharing of electrons, all of these atoms are now stable. And you can see here the signs that show this is a double covalent bond, these are single covalent bonds. A coordinate bond is when an atom provides a pair of electrons or more than one pair to another atom. In this case, a positive hydrogen atom is positive as it's lost an electron, and hydrogen only had 1 in the first place, so now this is an empty shell. It is now covalently bonded with nitrogen, and nitrogen has already covalently bonded with hydrogens that did have 1 electron. So nitrogen's now given its 2 spare electrons to the hydrogen, now giving hydrogen a full outer shell. Now it's stable, resulting in a complete shell. Thank you for listening to my presentation. Here is a list of the references that I've used throughout the presentation, and I've also got a bibliography, as I did look at a few more websites just to provide some extra information to make sure I was on the right track. Thank you for listening to my presentation. I hope you enjoyed it. Thank you very much.